I probably put far too much stuff into this talk, and I also want this not to really be a talk but rather a lecture. So assume, like I like this style from David on Tuesday, I think it was, where he had more of a conversation with the audience than just standing in front of people presenting things. So assume that something is not 100% clear. As soon as you have questions, please interrupt me, and then we can discuss them. If they get too deep into the material, we can just, I have all the papers here, we can do it afterwards, after the lecture. So this is what I want to do. I want to go from, the introduction is from another angle, not from biology, but rather from deep learning, what the people that quote-unquote real machine, or that do quote-unquote real machine learning, do. Then I want to introduce Boltzmann machines, which are one of the building blocks for these deep learning architectures. Go towards learning in Boltzmann machines, how you can do that, and show you that actually the math there is very straightforward and very easy to do, and also to show that for this, or in order to perform learning in Boltzmann machines, we need sampling. Then I'm going to introduce that, and then finally show how actually you can implement sampling from binary probability distributions with spike neurons, and afterwards even with stochastic LIF neurons. And if you then have time, which I don't think you will, I can also go into some deeper learning concepts. So first, introduction, deep learning. We heard the talk from Anders yesterday. That there is a hype wave for everything, and I tried to look for deep learning in that figure, and I didn't find it. But deep learning is currently, when it comes to machine learning, I would say one of the key words. It's like an all-purpose machine learning tool, because for the first time, you don't really have to engineer your feature vectors. Usually when you wanted to perform some sort of learning task, it was a real pain to construct and implement the filters, the Galois filter or stuff like that. But here in deep learning, we just use a large sets of nonlinear nodes, and they use relatively simple update rules and are still able to learn rather complex problems, especially because, like for instance here, you can see that some nodes in the lower levels focus on stuff like diagonal lines, and then as you get deeper into the architecture, you see stuff like phase nodes or even cat nodes emerge. There are many tasks or many applications for that. Like computer vision is one of the main ones, when there's speech recognition, natural language processing, and even stuff like dimensionality reduction, where you force the network to represent an input image, for instance, with a very small hidden layer, and therefore get a very compressed representation of the corresponding input image. Then others like drug discovery and toxicology, where we can just learn, or in gene expression graphs, where you can just learn like some other, maybe more known examples are like IBM's Watson and one. The Jeopardy constant, the Google self-driving cars, the glasses, and even stuff like Google's deepface garnered some recognition some years ago, because that was actually a task where you would find a face in an image, you would transform it to have a front facing, learn with a deep learning architecture. And the interesting thing is, or the question that was then asked, you get two pictures, and you have to decide if it's the same person or if it's a different person. And their architecture by Facebook actually reached human level areas of recognition. You see here even in the higher regions, algorithm arguably even perform better than humans. Further application that was actually like a few months ago, where the popular science titled it Dreaming Computers. We actually had a picture of that also in yesterday's talk, where you basically, what it actually is a tool for visualizing what deeper layers in the network actually learn. So you present an image, and then you tune the input weights to make a certain node spike in the network, and then you get some sort of input images. And if you do that continuously, you can see that like some nodes recognize something that wasn't there, and it has been titled as dreaming computers because they just produce new images by the machine itself. There are many architectures that I really do not want to talk that much about. There are the deep neural networks where it's basically just you present an image, you look at the output, and then you use backpropagation to just tune the network to better represent the output that you want. There are deep belief networks, which are basically just stacked Boltzmann machines that actually give it generative, or that are generative, so they give probabilistic answers about the problem that you want to model. And there are convolutional neural networks, which are also used in deep phase, where you have additional layers that are just like the visual cortex, where some nodes of the convolutional layers just perform their filtering operation over a small local subset of the previous layer. Then there are max pooling layers that just take either the average or the maximum of a certain subthreshold to make the network more robust to small shifts in the input. Then most of what I'm going to talk about today is going to be feed forward, so you present an image and then you get an output at the end. There are also recurrent networks that are mainly used for speech recognition, but all these networks have in common is that it is layers of very simple nodes that just perform tasks like these. So some years ago, the generally used one was a tangent hyperbolicus. What I'm going to present today is just a sigmoid function where the input is just a weighted sum of the inputs. And what actually most of the people in machine learning are currently using, or in computer vision, is just the rectified linear unit where you just cut off the negative part of the input. And apparently this is enough nonlinearity introduced in the system in order to perform all of the tasks that I just presented to you. So onwards to Boltzmann machines. What is a Boltzmann machine? It's basically, many people know it from physics. If you have that background, it's just you have a couple of, if you don't see my one you have a couple of binary random variables, so they can either be 1 or 0. And they are all, in case of a full Boltzmann machine, they are connected also. So you have only up to second order interactions, and if you look at the corresponding probability distribution, you see this here, then you can actually identify an energy for each for each state, and the energy is heightened or is lessened by a way that both of these neurons are units, which is called a unit, are active. Plus, there is for each node there is a bias term. So if this node is active, the energy is again reduced or increased if the bias is negative. Then there are restricted Boltzmann machines where you force your graph to be bipartite. So there are two layers here. There is usually a visual and a hidden layer. And the graph is bipartite, so there are no connections within a single layer. And therefore the energy function simplifies a bit. There is no 1/2 here because you don't summarize over all indices twice, and you get own excitabilities for the hidden and for the visible layer. And then you can just set them up and you get to the so-called deep Boltzmann machines where you just have here it's 2 layers, but there can be even more. If you learn, or if you perform learning, which I will present in a minute, you see that the higher you go in the hierarchy of the Boltzmann machines, that higher visual layer or higher hidden layers just tend to code for more complex patterns. So at the beginning with the cat and the human face.
Excuse me?
Yeah.
On the fact that there are no lateral connections anymore,
Mm-hmm.
does it change the ability of the network, what it can learn, and what kind of information it can encode?
It does change what the network can learn, but it actually makes the problem a whole lot more tractable. Because if you want to compute like a marginal probability distribution of a single layer given another layer, it is completely independent for each node, and that actually makes the problem tractable. And then, of course, the last thing, if you want to add labels, you can just attach them to somewhere, so you can attach them to the deepest layer and just read them out. Sometimes you also just attach them to the visible layer as like another quote-unquote pixel that is then just active for the corresponding input image. And then you can perform classification by just presenting the image itself and look at what label node is active for the most part whenever you do that. Now, what you can see that I don't know if I'm still not sure if you can really see that well in this example, that the more layers you have in your network, the higher the features that you can extract, and the more the better the images the network produces when it quote-unquote dreams. So for instance, here you see training examples of the MNIST dataset, so just a dataset of handwritten digits that is one of the default training datasets for these kinds of examples. And you see the comparison between the 2-layer Boltzmann machine and the 3-layer Boltzmann machine. You see that the generated training example or the generated images that you obtain from the network are a bit more crisp and a bit more or less blurry, so to speak. Then just what I'm not going to talk about, because we want to focus on spiking neurons, is I'm not going to talk about all these crazy machine learning techniques like pre-training, fine-tuning, and in general all this black machine learning magic, as I like to call it, because that would just need too much time.
Sorry, but can we? So, if you have, for example, 3 layers, right? What you do is that like you have like some input coming, and then for learning, what you do, like for example, if you have 3 layers, you look at like the output of each layer, and then try to train the.
That depends. So you can, but what you can do with like a 3-layer Boltzmann machine is that you first train this one, and then use the learned marginal distribution of this network as the input for the next. What then happens is that you don't get a deep Boltzmann machine, but rather a deep belief network, because only the first 2 layers are actually forming a Boltzmann machine. Theoretically, all the other ones are just feed-forward connections from the top down, which can still perform classification and stuff like that. It's just not a real deep Boltzmann machine, but rather a belief network. What you also can do, which I'm also not going to talk about, is to do some variational methods where you can show like the way you update the weights between the nodes improves the lower bound of the log likelihood or the objective function, which I have not talked about yet, but will in a second.
And this is the reason why, like, when you have 3 layers, the performance is better? Or?
No, first you learn, so to speak, like features of the input itself, and then you learn features of features and features of features. Like for instance, these could be corners or some lines that are present in the image, and then you learn some combinations of lines or combinations of corners, and then you learn combinations of that, so you can just go deeper and deeper and deeper and just learn more complex features. So exactly. So let's go to learning in Boltzmann, because I don't know the background of all of you. I'm just going to go through 3 very simple rules that you need to know when you deal with probability. The first is just the sum rule. Probability sums to 1, yes, and if you sum over a certain variable, you just get the marginal. The product rule is also very simple. If you have a probability of 2 things occurring, it is the probability of the first thing occurring, and then times the probability of the second thing occurring, given that the first thing has already occurred, or the first event or whatever. And just the transformation of that is actually the very known Bayes theorem that the conditional probability of of an event y given z is just the ratio of the joint probability given and the margin probability. You can see that here, if you know you're going to be in this circle and you want to know, given that I am in this circle, what is the probability that I'm also in the blue circle? That's obviously the ratio between this region and the whole red region. And then what we also need is the Hilbert-Leiber divergence. Who of you has heard of that at some point? It's like the general, it's not a measure because it's not symmetric, but it somehow assesses the difference between two probabilities. Say you have P and you have Q, two different probability distributions over the same alphabet, it's just the number of events or whatever. And say you want to find the ideal encoding, so to speak, or you assume the alphabet that you observe, Z, is distributed with a distribution Q, but in reality, which you don't know, it is distributed with another distribution P. So the ideal encoding length from information theory, Shannon theory, is basically proportional to the logarithm of the inverse probability. So for instance, if you would encode it in bits, and you have an event, or you have a letter in your alphabet that occurs half of the time, you would always use the first bit in your data stream to encode, do I have this event or do I have any other event? So that would be, therefore, the ideal encoding length for an event with a probability of 1/2 would be 1. And since it doesn't really matter which logarithm you use, we use the natural logarithm here, and so you get this encoding length. And so if you now think about it, you think your distribution is, your alphabet is distributed with this, but in reality it is distributed with the other thing. So you get an overhead. Because if there is an event where you make the encoding very short, but it doesn't occur as often, you're wasting space in your transmission, or in your data transmission. And on the other hand, if you make the encoding very long, but the probability of that event occurring is very high, you're again wasting space in your data stream. And the Hilbert-Leiber divergence is simply a measure of quantifying the average overhead. So you have the encoding of your single event, and you have the ideal encoding, the overhead, and then this is just the average overall possible event, which is then the Hilbert-Leiber divergence. It has some nice properties. It is always greater or equal to 0, and it is only 0 if the two distributions are the same. But on the other hand, it is not symmetric, so that's why I said in the beginning it is not a distance measure, because a measure has to be symmetric. So what we now do in maximum likelihood learning in general is we have a true distribution of our data. We don't know it, we can only observe it through some form of samples or some sort of input images, and then we denote with P star over V. So it's like a distribution over our visual layer that we want to represent. So what is the natural or the most natural thing to do? We want to represent this, but we only have the probability distribution that our model gives us. So this is the PV given our model parameter theta of some kind. And if you just do the calculation, you can see that you can just split the logarithm. You see that here we don't need to care about this vector because it's independent of theta, and we just replace the minus and the min with a simple argmax, and then you just get a regular maximum likelihood. This term here is called the likelihood because it just is the likelihood of observing, or the average likelihood of observing our data given our true data distribution. And because we still have the hidden variables, but we don't observe them in the data itself, we have to sum over them, which will be important in a minute. And this is like I think the most complicated slide I have, which is still not that complicated because it's very straightforward. Like this is all you need to know about how to learn with Boltzmann machines, which I find pretty neat. So you take the probability distribution that we have up here, and you just throw it in to compute the gradient. We want to improve the gradient, we want to maximize it, hence we just compute the partial derivative with respect to the model parameters. If you do that, you get two terms because product rule. The first term just gives you the vi and the hj because it just is the exponential. The exponential and the partition function itself form this in both terms. And the nice or the important thing now is that if you derive the partition function by the model parameter, you get once again behind hj, but you also get the probability distribution over different set of different set of random variables. So these are not the same variables as the actual visual data we need to sum over this. And because of that, like this here just gives base again, gives the probability distribution or the conditional distribution of the hidden variables given the visible data. And here we see that everything here is not these are different variables than this, so this just sums to 1. And basically this term becomes completely independent of whatever data we observe. So this can be called the model distribution or the model response. And here we just have we have the distribution over the truth data distribution given, and we have to multiply it with the conditional distribution of the model, hence the data term. And what that means is that if we update the parameters now, we just go into the direction of the gradient. You can do the same derivation for the excitability and arrive at roughly the same update rules. And what does that actually mean? Like in reality, you would need to compute the average for all the inputs, for all possible input values, and you would need to compute the whole probability distribution, especially for large-scale Boltzmann machines. You can see the number of values or the number of states in the Boltzmann machine scales to the power of 2 to the power of nodes that you have. So this is very infeasible for large-scale Boltzmann machines. So what you actually do, and what the guys at Google came up with like 10 years ago, is to just sample. So what you actually do is you have some sort of training sample, an input image, whatever, and you initialize your visible layer with that data. Then you draw samples from the conditional probability distribution and get a state, just one state for the or one configuration for the hidden layer. And then you just repeat this n times. So you just sample the visible layer again, sample the hidden layer again, sample the visible layer again, sample the hidden layer again. And in the end, you just say, okay, now I have these, and now instead of computing any averages here, I'm just going to take my sample value. And that is the first two, what you initialized in the beginning, that's your data term, the first sample. And what you receive after n steps is the model term, and you can actually show that this then leads the whole update scheme is called contrastive divergence, and actually works surprisingly well. So even just drawing one sample, you're just initializing the data, you're drawing a sample for the hidden layer, you draw one additional sample for the visible layer and one additional sample again for the hidden layer, so you have like a chain of four steps. That works surprisingly well. You can show theoretically that it is not optimizing the true gradient or actually any gradient, but rather a difference of DKLs. But nevertheless, it works surprisingly well. It's a very simple update rule. You just draw two samples, and your network starts to represent your input distribution. Then there are, of course, several extensions to that, but where you just, I don't know.
What was the A parameter, the bias?
The A parameter is the bias term of the visible layer.
So the visible layer is a bias term.
Yeah, exactly.
There's only the Markov bias.
Yeah, like there are the weights between nodes, and there is like the intrinsic excitability of each each node, so to speak. And there, because we have here the hidden and the visible layer, we have the A parameters are the biases of the visible layer, and the B's are the biases of the hidden layer.
Sorry. So do you know if anyone tried to like solve this analytically, not really with this learning? Because like what I know from physics is that there are like many good approximations.
There are these variance-based methods where you just say, okay, we try to compute a lower bound for the whole objective function. This is actually how they train the deep Boltzmann machine. And then you can just show that it improves and improves the lower bound of the grade. So there are, but it's still not analytically, and it's oftentimes it's still intractable. So the nice thing here is, as I will show in a minute, that we don't need to compute any partition functions, because if you just sample from the conditional distribution, as I showed, because there are no connections here, you can just do it essentially in parallel. And it becomes very tractable, and you never need to sum over all of the states of your network. Exactly. So what is sampling? It is just instead of representing or calculating the whole probability space of your function, you're just drawing singular samples, and oftentimes the relevant portion of your probability space is actually rather small, so you can represent not really. Okay. Can you see that? I hope. Because I can't bring around. It's not just. Yeah. Oh. No, yeah. Give me 5 minutes before I shut down. So yeah, exactly. We just draw samples, and this process is usually called Markov chain Monte-Carlo sampling, or MCMC sampling for short. It's used in many applications. Well, we have a target distribution P, which would in this case be our conditional distributions that we want to draw samples on when training Boltzmann machines. And we just, instead of just sampling each time from either sample, we just draw a series of dependent samples. So we have a transition probability where our next sample that we draw or the probability of drawing our next sample just depends on where we were in the last step. So the whole series of samples forms the so-called Markov chain, which first order Markov chain, which basically means that only the last sample influences where we go next. A very regular or one of the default models or update algorithms here is called Gibbs sampling, where you just draw a series and you just enumerate the variables in your network in any order. And then you just draw a new sample for the first one, given all the other ones, and then you go to the next one, update that one. So the conditional distribution for each of the k variables that we have is just dependent on all the others, whereas all the ones that are indexed lower are already updated, and the other ones still have to be updated. And by that, because we're only doing conditional distributions over a single binary, or it doesn't have to be binary, but in our case it's binary, so we only have to compute two variables. So the partition function there is just the sum of two factors, and that is very quick. And the things you need to show, just very quickly, is that you actually, in order to sample from the correct distribution, because you still want to do that, is that you are not changing the probability distribution anyway. So if you start at any state Z, you should not alter the probability of arriving at any other state or if you start as that prime, then it should not alter the probability of arriving at another state. And the second thing that you need to do is elasticity, which just basically means after I draw an infinite number of samples, I actually represent my target distribution. And if you do that, then you can also show that P star is then the only distribution. Like there is, for each Markov chain, there is only one stationary distribution, which will become important later. And this can actually be done with spiking neurons, finally. But why should we calculate? There is this sampling hypothesis, which kind of says that if you look at the dark rabbit illusion or at the Necker cube here, what you will notice is that you either see the rabbit or you see the duck. You never see like some sort of anthropomorphic double animal that is both a duck and a rabbit. Plus, you only see, or also here, you see either the orientation where this part of the cube is in the front, or you see the orientation where this part of the cube is in the front. You never see like a sort of superposition. And this, while this does not say that what I'm going to show you about neural sampling is actually taking place in the brain, it does suggest, however, that the brain is also not computing probability distributions by itself, but rather is sampling from the set of possible explanations for a given visual input. You just jump from state to state, and you don't compute like the whole superposition. How do you do that in terms of neural sampling? Using it, I showed that you can actually or see the sampling dynamics of any neural network as samples or as samples from a binary probability distribution. So each neuron, whenever it fires, or for each neuron there is an according binary random variable. And whenever the neuron fires for a certain amount of time, which is usually the refractory period, the corresponding binary variable is set to 1. And after that, it just decays back to 0. So at any point in time, you can just ask, what is the current state of my network? So for instance, here, just the first neuron spike, so it's 100. Here, all 3 neurons spike, so it's 111. And here, only the first neuron did not spike, so it's 010. And each point in time basically defines a valid sample from the underlying probability distribution. And the nice thing is, if you then want to compute marginal probability distribution, where you only look at a subset, all you have to do is just look at that subset of neurons and only compute the states for that. So you don't need to, you basically get the marginalization for free. What we have to do, or what using it, I'll show that the only necessary condition for that is that you define an arbitrary or an abstract membrane potential. And what this membrane potential has to encode is basically the log odds between the given neuron, between the given binary variable being active versus the given binary variable being inactive, given all other nodes in the network, which, if you turn it around, results in a sigmoidal activation function. So the higher so basically a sigmoidal shape, so the higher the corresponding membrane potential, the higher the activation probability, or the higher the probability of finding the neuron in an active state. And how do you do that? You have to also, again, you have to define your Markov chain. They do that by just introducing some latent variables zeta that basically turn the problem into a first order Markov chain again, because you can imagine you have a neuron and it spikes and then it is active for, if you go in a discrete time scale, it is active for tau steps and then it decays again. So where you are in the refractory period, you have to know where you are in the refractory period. So you need to have a random variable that actually tells you that. So whenever a neuron spikes, we set the zeta to tau, then it decays deterministically, which you can see here that the transition probability for a given zeta to the next day if we are this is 1, so it decays deterministically, and then only once we are here, once we are at 1 or at 0, we need to be, if we didn't have this here, then we would always have at least one step where we are inactive. We can spike again. I'll just leave that.
Sorry, do you have a number that how long would it take, like if you want to have, like 1 million samples for let's say 100 units? Do you have a number, like how long does it take to do?
Well, every time step defines a valid sample.
Yes.
And so you would need to wait 100 time steps. Or
like how much time you need to for like finish this sample, like get 1 million sample?
I'm not sure I understand.
I just want to know the performance of this sampling you have, like how long.
Well, that depends on your underlying simulator, right? Like it depends on what your neural dynamics allow for.
Okay.
I mean, this is just, we were just talking about an abstract Markov chain, where you just, every neuron has this. What you basically do is, in every time step you ask yourself, do I spike with this probability? The log t is just to normalize because we're in discrete time, so the smaller the time scale, the lower the activation probability in each time step. And then you just run the network, and you just, like, in each time step you ask, has the neuron fired? If it is in an active state, you just decay the zeta variable by 1. And if it isn't, you look at the current membrane potential and see if it's fired. And then you just run the simulation, and that is actually pretty fast. Like you can just do it on a regular desktop machine or.
So the upper part of the circle is the refractory digit.
Exactly.
And it corresponds in the previous slide to when you say the neuron is active.
Exactly. This is basically this
part. Okay. So the spike is the black line, and the gray part is the.
Exactly. It's the refractory. Exactly. Because as you can see here, the state of the binary is obviously completely determined by the state of the z variable. If it's 0, then we are inactive, and if it's below, if it's above 0, then the binary variable is active. So you could actually also just or omit the binary value, just formulate it in terms of the zeta variable. And then you can actually show that this transition operator that I just showed you with the helper variable zeta leaves the corresponding distribution over binary variables invariant. And the nice thing is, for the abstract neural model, which has rectangular PSPs and stuff, I will come to that. This inference is exact. So if you look at the DKL of the reconstructed probability distribution from the samples, it will go down to 0 if you just wait. Long enough. We can also show the irreducibility, because you just think of within the refractory period, you can just have theoretically all neurons go to the base state, then you are at the 0 state, and then every neuron can basically fire with some, albeit small, probability, so you can still reach all of the states in your state space. However, the dynamics are, I didn't talk about integrals, I shouldn't probably talk about that. But what a nice thing is, that you can also prove with a very rigorous mathematics, is that each neural network that is sufficiently stimulated in a stochastic manner is sampling from a stationary probability distribution towards which it will decay exponentially fast. This is a nice paper by Heidelberg et al. Where they demonstrated that. So whatever, like as long as you have stochasticity, or as long as you have sufficient stochasticity in your network will sample from something. Oftentimes you might not know what that is, but still, like from a theoretical standpoint, it does that. Exactly. So for now, we just talked about the neural computability condition, and the nice thing here again is that it holds for arbitrary distributions of binary variables. They can be as complex as you want. But the problem is a bit that if we are limiting ourselves to the neuron case, that those interactions are mostly in this, like, if we talk about point neurons, they are saying about one neuron fires and the other neuron sees it, and there is no interaction of a third neuron. And so the straightforward thing is just to grab the Boltzmann distribution and insert it into the neural computability condition, and then you see that basically the abstract membrane potential is just a linear sum of the state of all other neurons with a certain weight, as you would expect from regular neurons interaction, plus the intrinsic excitability of the corresponding neurons. So this is very reminiscent of neuron interactions, but you could think to implement, like, for instance, dendrites or higher order probability distributions where you have like the W, J, K, I, where you have the Z, J, and Zi, where you only have this factor of both neurons are active. Stuff like that. You can, that is a nice thing, you can throw whatever you want into the neural computability condition, and you get, as long as your neurons follow the resulting membrane potential dynamics, you sample from the correct distribution, which I find pretty.
Sorry, is it a still Gibbs sampling? So
it is basically Gibbs sampling, yes.
Okay.
It is Gibbs sampling with non-reversible dynamics. So you just have to, as soon as you enter the active state, you have to wait for a certain amount of time, and then you go into the inactive state again. Whereas in Gibbs sampling, you just check, do I enter the active state, and then in each time step you just check, do I enter the inactive state again. So Gibbs is just more than in that case, or in that regard. And what you can then model with that is things like perceptual model stability, which is just when you have like both eyes get different gradients, so they are it's two different inputs that you want to explain, and you can they showed that by having a hexagonal grid of neurons, which each had a certain tuning curve towards certain orientations of the shades that you see, and neurons that had a similar orientation had a strong or a high weight connecting them, and neurons that had a different different orientation that had a low or even a negative weight connecting them. Then you can see that when you just let the network run, you see it samples from all the states. But as soon as you sort of impose a certain gradient, like in this case 45 and 135, 45 and 135 degrees, where they just fixed some neurons that had a certain orientation, like green and purple, you see that the network is only sampling from these states that correspond to these orientations. Furthermore, you can do probabilistic inference in Bayesian networks, where I don't know if any of you or if you know the Knakerston optical illusion, where you see here the intensity profile of the shading of both images are the same, but here you see two hands, and here you see two rectangles, and because of the shading, you infer a certain 3D shape, which again then infers a certain relative reflection. So here you see that this is clearly brighter than that, or that there are, and here you see that they are both basically receive light from the same light source. And you can model that in a Bayesian network, where you just have where you again have certain neurons, each representing one of these binary variables, so whatever you nodes. But you have to somehow model the interconnections a bit different. Don't want to go into detail here, but it's basically you have to model for each state of the other two neurons, or of the other neurons, you need to have some sort of interconnected neuron that model the relative probabilities. And as you can then see here, the probability of, for instance, here, if you have a certain element that the contour here is shaped or curved or straight, you see a different probability for the relative complexity. Here is in black is the theory, and in blue and green are two different implementations of this Bayesian network. And you see that still there is a great overlap between the two, between theory and simulation. And you can even switch it during a network simulation where you just switch off the shading, and then you see that the network infers the correct thing once again. What you can also do is solve constraint satisfaction problems. So here you have again for each your network basically consists of many winner-take-all networks. So I think every one of you knows Sudoku. So here in each row, in each line, and in each box, so to speak, each 3x3 box, you can only have one, or each number can only appear once. And so for each small digit here, we have effectively 4 winner-take-all circuits. One says that there can only be one digit here. One says that there can only be one digit in this line, and one says one digit in here, and one again in the corresponding 3x3 box. And what you then, or what you can do then, is have this network actually solve Sudoku. So an active neuron basically says, okay, I think that the corresponding digit should be here, which via inhibitory weights causes the corresponding nodes in the other winner-take-all circuits to have a lower probability to spike. And at some point, for instance, if you look at the performance here, you see that at some point the network will, or it's not guaranteed, but in many cases, it actually then finds a probability or a configuration where every constraint is satisfied, and then by a mechanism that I don't want to explain right now, just locks into that node, and thereby you can use these stochastic neurons to solve basically constraint satisfaction problems. Although it doesn't work all the time, like if you look at the average performance, it always finds approximate solutions, like good approximate solutions, where like 90% of the constraints are validated, but it still takes some time to go into the to finally find the one configuration that actually solves. So here you see the solve path. And now finally, because I only have 10 minutes left, I want to show how you can actually perform these things with stochastic LIF neurons. So, I don't know how many of you were in the talk of Tom on Tuesday, where he introduced you to basic neural models, but I think everyone should be familiar with the conductance space, leaky fire. Neuron, you basically have a membrane that is pulled towards the resting potential unless there is some synaptic input, where each synaptic input is basically, or each spike that the neuron receives increases the conductance towards one of the reversal potentials and decays exponentially. And whenever we cross a deterministic threshold, the neuron spikes, we remain in the factory for a certain period, and we reset the membrane potential afterwards towards a certain reset level. So this model is inherently deterministic. There is no stochasticity, nothing. But what you can do, and what's been shown that you can do, is that if you have strong synaptic input, you can actually reformulate the dynamics of the LIF neuron in the form of high conductance state. So here, the neuron actually follows some sort of effective potential that is driven by the synaptic input with a certain effective time constant that gets lower the higher the total synaptic conductance is. And you can just, you can then perform the first order first order Taylor expansion and see that basically the membrane potential is just a linear transformation of the synaptic input. So this here is the synaptic input. So you see it's only a factor and an offset. And so the membrane potential is basically, in this case, a linear transformation of the synaptic input. And the synaptic input is, because we just use diffuse Poisson noise, it basically does a random walk. So whenever there is an excitatory spike, we just walk in the upwards direction, and whenever there is an inhibitory spike, we walk downwards. Every physicist should know the term Brownian motion, which is just that. And the nice thing is that you can describe that with an Ornstein-Uhlenbeck process. So what that says is we have a mean towards which our random process decays with a certain time constant. Plus we have a linear process, which is what I just showed you, where it is just an undirected random walk into any direction. And if you do some math, then you can identify that actually the mean that we are drawn towards is the effective membrane potential, where this is just, if we are using Poisson noise, we know what the mean of the noise will be. So we know what the effective membrane potential will be towards which we are pulled. And we know we can identify the covariance matrix for the corresponding, or the covariance for the corresponding linear process. And once we know that, we can describe the membrane potential or the membrane dynamics with an analytical treatment, which I don't want to go into detail, but what you actually do is then, if you want to compute the activation function of your LIF neuron, is you need to go from one deterministic point towards the next deterministic point. And so what is or where your membrane distribution is well defined. So what is the only way you can see that is when you just cross threshold, in which case your membrane distribution is a delta function. You know your membrane is at that point, and you can put that into the Ornstein-Uhlenbeck equations and just see how will that evolve over one refractory period. If after one refractory period the effective membrane potential is still above the threshold, the neuron will simply spike again. So it's a so-called spike burst, and then you just do that repeatedly and basically until infinity. You just stop after it's already okay to stop after 5 or 6 spike bursts. And by this you can compute the you can see this here. So here we have the prediction in green, and or in red actually, and the corresponding measurement of of the simulation in test, I think. And what you can then do is just vary the resting potential and see what the activation function is, and by that you can find a relation between the biological and theoretical domain. Because in the theory, if the membrane potential is 0, you have a probability of 1/2 to spike. In reality, that is not the case, so you need to fit that somehow, and once you have fitted that, you can just find also for the weights a way to translate the corresponding parameters. If you do that, you can just look at a random Boltzmann machine and compare theory and just the obtained or the reconstructed probability distribution of the network, and you see that there's a log scale plot, and still there is a very fine or a very good correspondence between the theoretical values and the obtained or the reconstructed probability. But what you also see is, if you remember from the abstract model, this is actually guaranteed to be correct. Like we sample from the correct distribution. So if you look at the DKL between the reconstructed probability and your actual probability, which you can still calculate in terms in these cases where you have only a few neurons, For the abstract neural model or for deep sampling, this would continuously go towards 0. So the longer you wait, the better your approximation becomes. But since here we have exponential PSPs, so you see that here, for instance, that we want to have this refractory period or this rectangular refractory period. What we actually get is this exponential. First we have an overshoot and then we have an undershoot. And what all of this does is just introduce a constant factor into the DKL that you cannot get rid of because you're essentially sampling from a slightly different distribution. You're not sampling from the correct Boltzmann distribution, you're sampling still from some distribution, as I told you, but it's not in quote-unquote correct Boltzmann distribution, so you always plateau out at some point. And you can combat that by, for instance, the better your related, or the longer the refractory periods are and the longer the synaptic constants are, the more accurate your reconstructed probability distribution actually becomes. And then you can again perform something that looks like the bistable stability. Here you train a Boltzmann machine to represent 3 images, 0, 3, and 4. And you introduce some evidence into the network, and if you just let it sample freely, it will just go towards, or just visit all of the modes of your probability distribution. But if you start to plan the middle part, where you say, okay, I want to, for instance, reconstruct the corresponding image, then you see that the 0 actually has no black lines here. So it actually gets suppressed. Then the network actually just visits the 2 states that are compatible with the input I presented. Furthermore, you can also do Bayesian inference with stochastic LIF neurons. It's basically the corresponding implementation to what I showed you before. There it was with abstract neurons, and here it is with actual stochastic LIF neurons. And here we also see like some more problems because if you sample with Bayesian, you have actually higher order interactions that you need to model somehow. I didn't talk, or I didn't go into great detail about how you do that. Basically, you do that with inhibitory interneurons or some other populations. And here it is very crucial that the inhibition and the rectangular, or that the PSPs are very much rectangular, and you can see here. This is the theory. These are the rectangular and alpha-shaped PSPs, but still the abstract neural model. And here is the LIF, LIF model, but with this kind of a PSP shape, and that is a problem. You see like a large deviation between what you want to infer and what you actually infer. And one way to reconcile that, and what they did in this paper, Obst et al., is that they introduced something that's called MLIF, where you just have basically a SynFire chain or a series of helper neurons that have a slight delay, one after the other, and a lower total amplitude. And by that you can just generate a more rectangular PSP, where the last neuron is actually then, like, say you want to have an excitatory PSP, then the last neuron would be inhibitory in order to pull down the membrane again. And this actually, like, has been demonstrated like some weeks ago by a bachelor student of ours. He implemented a network that worked like this and had the synaptic interactions between sampling units, basically in this fashion with SynFire chains on a spiky chip that some of you used. It was a Boltzmann machine with only three or four random variables, because there are not that many neurons on a single spiky, but nevertheless, that is was the first neuromorphic implementation of a Boltzmann machine that I know of. And I think since we're already past 3, we will not go into spike-based exploitation maximization. If some of you are interested in that, I can talk to you about it afterwards, and now I will just open the floor. For questions. So what I want you to take away from this talk is basically that Boltzmann machines are a vital building block for building deep learning architectures, especially like up until a few months ago, they were actually what Google mainly used. You can then interpret the spiking network dynamics of any network as drawing samples from an underlying probability distribution over binary units. And this is applicable to many things like Bayesian inference, constraint satisfaction problems, and learning. And you can do that instead of just doing it with a for instance, if you want to implement it on Spinnaker, I would probably guess that you can just use a stochastic or inherently stochastic model. On the Heidelberg hardware system, this is not possible, but now we have a theory that makes it tractable to implement that on the brain scales, not brain scales, the human brain project hardware, and it has already been done on the strategy. What I didn't talk about was how you can then perform expectation maximization with these spike waves.
Thank you.